Thanks a lot, Amy. So we can now move to the questions. If anyone has any questions, can you please raise your hand?
Well, I could ask a question, Amy. I was just giving you a clap, but
sorry.
I will ask a question anyway. So you mentioned turbulence, and I was just wondering how much work has been done on the interaction of acoustic modes with turbulence.
Not much. So we've looked at acoustic waves. So obviously where the acoustic waves are generated is at the flame, and then where they generate noise is at the acceleration zone, which is at the downstream end of the combustor. So we've been quite interested in how the acoustic waves get through all the turbulence in the combustor to the downstream end. So we've done some modeling for channel flows, and then we've also done and CFD simulations, and then we've extended that more recently to real combustor flows. So trying to develop simplified models for the shear dispersion process due to both the mean flow and the large scale fluctuations. Right. So we did it computationally with modeling, and I believe the group in Zurich, led by Nicolas Noiret, just did some experiments on that quite recently.
Okay, thanks, that's interesting.
There is a question from Alison. I don't know, Alison, do you want to ask your question?
I can do, yeah, I typed it in the chat, but yeah, our question is around possible changes when we move to hydrogen as a fuel, in that we're more likely to see designs based on diffusion flames rather than premix flames, and whether that changes kind of processes that you're talking about.
It may well do. So we're starting to look at kind of very simple models for laminar diffusion flames, so going from level set type approaches to Burke-Schumann models, but we're just really at the very start of that. So you would probably know a lot more than I do on the differences between the diffusion and the laminar flames.
Not from an acoustics point of view, definitely not, no. But
yeah. So certainly with reaction engines at the moment, they're quite unclear with their hydrogen combustion whether it's going to look more like a diffusion flame or a premix flame. So at the moment we're quite open. We're quite interested in doing some really quite fundamental work and comparing it to DNS, where they've got all of the kind of Lewis number effects, the flame front effects, the density change effects, everything in there, and seeing what level of modeling we can do for both diffusion flames and premix flames. At the moment, even the really basic stuff seems to be open.
Should be interesting, I think. Thank you.
There is a question from Dave Abbott. You want to ask your question, or?
Yes, I was. You've mentioned in your future work the impact of thermoacoustics for hydrogen and ammonia, the low carbon systems. Can you say something about why hydrogen may be worse than other fuels, and what we can do about it?
I mean, these are huge questions, aren't they? So, I mean, I guess it's how you generate hydrogen in the first place, how you transport it, the safety implications. I think from the combustion point, so hydrogen's got a really different density to all the other fuels. It's got a really different laminar flame speed. So all of the kind of technology and scientific and engineering knowledge that's been developed for fuels like methane and kerosene, you've got to go right back to the start for hydrogen. I think for ammonia, things are a lot more familiar, but hydrogen is just a completely exceptional fuel in lots of ways. Obviously, if you can generate the hydrogen in a green way from excess wind power, and you can transport it cheaply and safely, you've got gas turbines potentially feeding into the kind of renewable energy landscape. But it is a very, very different fuel to everything that people have been working with in the past.
Yeah, but thinking about, as you say, the potential for there being some hydrogen about. So there's a lot of interest in blending hydrogen into natural gas. When is that likely to have a significant impact? Is it at 5%? Is it at 50%? Do we have any feel for how hydrogen is actually going to...
we've started looking at this for simple laminar flames, and what we're seeing, basically, if we look at the flame transfer function, how the flame responds to acoustics for a laminar conical flame, we're seeing that frequency response, so you end up with a drop off in gain. You've basically got a low pass filter that your flame acts as. The more hydrogen you put in, you push that cutoff to higher frequencies. And so that's quite worrying acoustically, because it means that your flame is able to show a large response up to higher frequencies. But this is all work going on right now. So, but
also you would expect the flames to get more compact, so sort of time delays to get shorter. Yeah. So the phase relationships would drive you to higher frequencies as well. Yeah. So you might be better off at low frequencies, but make things worse at high frequencies.
Well, at low so we're seeing the same gains at low frequencies. I'd have to, obviously the phase, it's difficult to predict what the effect of phase on stability, because it's depending on all the boundary conditions as well, so that it's not as obvious.
Yeah, no, I agree, it's not as obvious, but you would still expect the shorter time delays to favor higher frequencies.
I agree.
Yeah. Okay. Thank you.
I see that there's a conversation sort of going on in the chat, but I don't know if Alexei wants to just ask the question.
Hello, can you hear me?
Yep.
Yeah. That's wonderful talk. Many thanks. I got maybe a very profane question. Your flame response model, does it predict any resonant frequencies for your flame? And if so, do they depend on turbulence? And secondly, does this flame model predict any saturation?
So the flame model itself, so because it's assumed that you're putting a flame, so I realize that you may get kind of flame front instabilities, which will eventually sort themselves out, but it's basically assumed that you're putting a flame that itself is stable inside an acoustic resonator. So the fact that we're using this idea of a frequency response says that we're assuming that the flame itself doesn't have any unstable modes. Obviously, if we're putting in a frequency, a velocity fluctuation at 100 Hertz, and we're saying we expect something out at 100 Hertz, you're assuming that the transients are all dying away, which wouldn't be the case if the flame was unstable. And yet we do it for, practical flames with lots of turbulence. We can apply background sort of synthetic turbulence if we're sort of shortening the domain. So all of that should be accounted for in the simulations. So we do some kind of quite big large eddy simulations, and we've worked with people like Bill Jones, who's kind of got a lot of experience in reacting flow and turbulence. Is there any follow-up? I don't know if I answered all of that.
So do you have or you don't have any Rayleigh criterion?
The Rayleigh criterion is about the thermoacoustic system as a whole. Yeah, so if you're just looking, the Rayleigh criterion is about the acoustic modes and how they interact with the flame and the combination of the pressure and heat release rate in the whole system. When we do our simulations, we actually just do it at the flame zone, and we actually also assume that the dominant flame response is to height. So the acoustic waves set off hydrodynamic fluctuations, vortex shedding, and the flame responds to the hydrodynamic fluctuations. So we actually just do an incompressible large eddy simulation. It accounts for density changes due to temperature, but it doesn't have any acoustic waves in it when we do our flame simulation. It's just a response. How does the flame respond to applied velocity perturbations? And it's not the whole combustor, it's just that really small zone around the flame.
If I may say one last thing, Aimee, there's quite a lot of work which was done in Leeds in the BOM on the transition of flames to cellularity. The spherical growing flames, in fact, they're quite peculiar in their instability onset. And the spherical combustion vessel is, in my view, quite an ideal tool to check your acoustics. And I wonder if the old results generated in this BOM for cellular flames would not be a good sort of a checkup for your flame models. Thank you.
Thank you. It sounds interesting. Does the acoustic stay linear? That would be my question.
When you look at the pressure oscillations in the bombs, they stay certainly well under 10% of the mean. Actually, they are well under 1%, a fraction of a percent, which I can't tell you off top of my head. But yes, it's a very acoustic oscillations.
Okay, thank you.
I think Ono had a question.
Hi, thank you for your presentation. What about acoustic control? I mean, as soon as you showed the movie, I thought, oh, can you trigger it the sound so that you can reach what you want to reach?
Yeah, so that's how I got into thermoacoustic instabilities in the first place. So through active control of them. So we've done active control with loudspeakers at one end. So you measure a pressure, say somewhere on the duct, and you feed that through a feedback controller, which you design, and then you force a loudspeaker. For bigger systems, you can force the fuel flow rate unsteadily, as long as it's not choked. And then for annular combustors, you need to deal separately with each circumferential mode. And you need to have multiple actuators and sensors. So yeah, I'm really interested in all that. That's how I got into it.
Is that feasible in the applications you're looking at?
So part of the control, I would say the controller design is quite feasible, and measuring what you need it to is feasible. I guess the reason I didn't go any further into it is because I felt like the actuator technology wasn't there, having high bandwidth actuators. And to get the kind of actuator power you need, you have to be working on actuating the fuel. So I kind of felt like the practical implementation was kind of lagging. That if I went any further, then it wasn't going to be that relevant.
Okay.
But that might have changed now. I don't know. I don't know how actuator technology's developed. I'd always be interested in going back in if it is relevant.
Cheers. Thank you.
There's a question from Xiaowan, if I'm pronouncing the name correctly. Do you want to ask your question? Or
hello. Yes, it's Sean here. Actually, I suppose when you asked the question to Alexia, part of that perhaps has been already answered. So really, I was trying to find out whether the assumption that acoustic wave, entropy, and vorticity wave are assumed to be completely coupled, how realistic is that assumption is. And then I have a second one, slightly detailed, about the modeling of the acoustic wave in a channel when the area changes. What boundary conditions that you've used for that computational domain, please? Thank you.
Yeah, so for the second one, we've done a few different sort of boundary conditions. So what we basically take or the easiest one to explain is that we take a loudspeaker forcing upstream. So I don't know if I can come out. Oops. So for this duct, you can connect it to a straight duct upstream and a straight duct downstream with constant temperature. So then you're really focusing in on the area where you've got a temperature and area change. You can apply, say, acoustic forcing upstream, and you can apply different boundary conditions downstream. You can either have non-reflecting or choked, whatever you want to use. So we've looked at a few different options. For the first part of the question, so you can so about the Chu and Cavagnet. So I think it was actually with the acoustic modeling was here. Yeah, so I mean, the assumption that they're uncoupled. So the assumption is that the A and the B propagate at the speed of sound relative to the fluid. That's good. And the fact that they're decoupled in a high Reynolds number flow from the entropy and vorticity are good. The thing that breaks down most quickly is assuming that the entropy and the vorticity waves, certainly the entropy wave is one-dimensional, and I guess vorticity wave, you have to think about the kind of direction, but again, assuming that it's one-dimensional, because if they're advecting with the flow, and even if you've got a high Reynolds number flow, you're going to get some sort of boundary effects. But actually that doesn't affect the acoustics very much. So it's fine to assume it in terms of the acoustics. It's just that if you want to take account of how these drop in strength, when you apply your conservation equations, you might need to just put it in an extra model that accounts for some dispersion. The effective Reynolds number of acoustic waves is really, really high. So they're very little affected by viscous effects in a geometry of this kind.
Thank you. When you deal with this low frequency range simulation, presumably it does have some interaction between the acoustic wave and the vorticity wave.
Not, I mean, if you've got an area change, then yes, but not just in a straight duct. I mean, a vorticity wave just moving by itself is silent.
Right. Thank you very much.
It's kind of when you distort it or it passes through an acceleration that it couples into the acoustics.
Okay. I think we went through all questions, unless there's anyone else who wanted to ask a question.
Yes, I want to add a question. Can you hear me?
Yep.
Yeah, okay, thank you. Thank you for your talk, Dr. Morgans. Are you doing or planning to do any work about intrinsic thermoacoustic modes? And also, are you working on hydrodynamic stability analysis on the flame? Because you decouple the acoustic of the combustion chamber and the flame transfer function, but are you actually working on hydrodynamic stability in specific on the flame? Thank you.
Yeah, so the second part first. So when we say we treat the flame, we're actually treating the kind of hydrodynamics and the flame at the same time, because we are kind of doing large eddy simulations. It captures all the hydrodynamics as well. So we haven't done a hydrodynamic stability analysis. I know people that have, but all the hydrodynamic effects should be in the CFD simulations. For the first part of the question, what was the question again? There was a word that I missed.
The intrinsic thermoacoustic modes.
Yeah, intrinsic. So they depend on the flame model. Yeah, they just depend on the flame model rather. So yeah, I mean, the low order network approach fully accounts for all intrinsic thermoacoustic modes. You put in your flame model and they're there.
Okay, thank you. Thank you.
Any other question?
If I could just make a couple of comments, it's Dave Abbott here. There was a question about active control. In large power generation gas turbines, Siemens did use active controls, and there are still some machines around with active control on that they had when they had issues on what is now the Siemens SGT 4000F machines. And the company that helped produce that system is still available commercially, and they will sell you an active control system for gas turbine combustors if you want one. So it is something that can be done, and that's a large annular combustor as well. That's something that can be done and is done. And there was another thing in the chat. Some people were suggesting that we may be pushed towards for hydrogen flames to diffusion to solve the flashback problem. But in most of the manufacturers of power generation gas turbines, they are developing effectively premix, many of them looking at micro premix systems. Some are looking at diffusion systems as well, but we don't necessarily have to go to diffusion flames to avoid the flashback problem.
Okay, thank you.
And I'd just like to say thanks to Aimee for a really interesting talk.
Thank you very much. Well,
if that's all, I guess Aimee also needs to leave at some point. It's 3:15. Thank you very much, Aimee, and thanks everyone for joining us for this last colloquium of LAFD into 2020, and see you all next year. Have a nice holiday.
Thank you very much for hosting me.